All right, well, I can go ahead and get started now and have people log in as they do. So my name is Vanessa Scott, and I am the Director of Corporate Relations and Innovation here at Scripps Oceanography, and I'm excited to be your moderator and host today for the Technical Forum. Douglas Alden, who is the chair for the Scripps Technical Forum and lead engineer for the Center for Western Weather and Moderate Extremes, would love to have been here today, but he is doing field work, so I am taking over for his place. We definitely encourage an interactive discussion, and we would love for you to enter your questions into the chat throughout the session. Our speaker, Chi Wang, has said that she would love for you, if you have some pressing question while she's talking at any point, to please raise your hand. We can unmute you and you can ask the question, or you can type it into the chat and I will go ahead and read it off to her. So definitely, we will also have time at the end for Q&A in case we don't get to all of your questions. Today's session will be recorded and available on our Scripps Technical Forum YouTube playlist on the Scripps Oceanography YouTube channel, and also be posted on the Scripps Technical Forum website, where you can also find more information on the group and recordings of past sessions. We also really welcome your feedback and suggestions on future topics and speakers that you'd like to hear from. So please feel free to reach out to either myself or Douglas to make those suggestions, and we'll go ahead and incorporate that. And without further ado, I would like to introduce our speaker today, Chi Wang, who is a research scientist at RBR. She's going to be talking about improving oceanographic data processing using Python with RBR. And with that, I will go ahead and stop sharing and hand it over to you, Chi.
Thank you very much, Vanessa. So I'm going to share my screen. Oh, is it okay? Okay, perfect. Yes, yeah. So hi, everyone. My name is Chi. Today, we're going to talk about improving oceanographic data processing, the Python RSKtools basics and demo. So our purpose is to give some basic demo to show you how this open resources toolbox works. And the most important is we want your feedback. Like, just let us know like what more functionality you would like to see in the toolbox, and what makes your life easier. Just let us know, and your feedback values to us. Okay, so I'm going to start. So my name is Chi. I've been working at RBR for more than 4 years as a calibration technician, technical sales marketing associate, and now a research scientist. So I was trained in physical oceanography in Dalhousie and Ocean University of China. And my research was more about ocean modeling and ocean waves. So I love ocean waves. Okay, so though I used to work at a sales marketing team, but let's get rid of that part. Let's jump into the technical part. What is RSKtools? So RSKtools, aka PIRSKtools, is a free and open resource sources toolbox written in MATLAB. So if you were like RBR user, you know, like our Ruskin RSK data files, they are SQLite databases, which is a very popular database engine. So these RSKtools is designed to read, post-process, visualize, and export RBR data. The current version is 3.5.3, and it's compatible with MATLAB later than 2013. And it doesn't require any additional paid toolbox like signal processing or statistics toolbox. Yeah, and why we develop pyRSKtools. So you may have realized that Python is getting more and more popular. And an important reason is it is completely free. But MATLAB, you need license. I still remember when I was a student and we used shared license. Like you have to wake up really early to get a license to use the MATLAB for the day. And also like not just the ocean community, we can see like in the job hunting community, like in US computer science lecture use, and also the questions from Stack Overflow. We can see Python is getting more and more popular, especially after 2014. And that's why we develop pyRSKtools. So still, it's a free and open source toolbox written in Python. It provides a direct connection between the RSK files and Python. It is compatible with Python 3.8 and later. And currently, we support the RSK files. If it is full type, then it's 2.0.0 and later. If it is EP desktop, then it's 1.13.4 or later. And we do have customers that still dealing with the data with previous RSK file version, and we are gradually getting there to support these old versions as well. And the latest version is v 1.1. Yeah. And here are some useful pages that you can use when you start with pyRSKtools. So first is about our web page, and here I'm going to show you our online documentation. So here you can see like the introduction, installation, and we have 2 user guides getting started, and more information focusing on the post-processing methods. And every method is documented here, including and also the channels, data tabs that you can explore more. And we have the our open resources on Bitbucket repo, and please feel free to look up the source code there. Okay, so let's get started. Just let me know and interrupt me anytime if you have any questions or if anything is not clear to you. So first, let's start from the installation. So one thing, the most part I love for Python is their free and multi-contributions from everybody and different versions. And also the part I hate most is the multi-versions, because sometimes it makes you crazy, like it works for this project but doesn't for others. So we always recommend to use the virtual environment. So this is the command line for the Mac user. I'm going to show some demo here. Like here, when I type Python 3 virtual environment, and let's call it my environment, and then you can see there is a folder created with the name my environment. And if you active that environment, you can start your virtual environment. So let's do it here, source. Okay, then you can see a small bracket in front of my command line. Oh, and this is meaning like I am in this virtual environment. And after that, you can start to do the installation using pip, because we have the package available in PyPy. And just a kind reminder for most of the Jupyter Notebook user. So once you set up a virtual environment, please don't forget to add this virtual environment as a Jupyter kernel, so that when you open a Jupyter Notebook and you go to kernel, change kernel, you can see the available virtual environment, so that you can select. Okay. So let's look at, give quick look about what methods we provide in pyRSKtools. So basically, we provide functions for read, process, view, and export. Sorry, am I hiding? Oh, and some other useful functions. Yeah. That you can use to copy, create, add channels, like some miscellaneous use. So in the pre-register form, I received some questions. I remember one of the question is asking, what's the difference between MRSK and pyRSK? So there are, generally speaking, they're the same, but just the small details are different. So when if you are an MRSK user, when you open the data file, you probably notice there is a structure. There is a structure called downsample data, but pyRSKtools get rid of that. Like when you do open in pyRSKtools, the data doesn't really populate. And we will see more details when we do the demo. But just we stop using the down sample in pyRSKtools. And also for the profiles, the data structure is a bit different. So I'm going to stop sharing and use my whiteboard. You see it clearly?
Yes.
Okay, awesome. Awesome. Okay, so this is MRSK, and for profiles, so when you do RSK read data, you read a time series of data. And when you do get profiles or convert time series to profiles, it restructure these data struct, RSK data struct from and reshuffle the structure from time series to profiles. But for pyRSKtools, it's always showing as a time series. So the way we grab the profiles is by calling this get profiles indices to grab the indices of each profile. Okay, so if you want to see, let's say this is RSK data, and if you want to read the temperature, and you just need to add the profile indices here. And this is the way you get the profile for temperature. And another difference is the way it copies the raw data. So before the post-processing, we always recommend the user to copy your raw data because you're going to do a lot of changes on the RSK. And for MRSK, you can simply use raw equal RSK. And this is just like a physical copy, like copy the RSK file to the raw structure. But for pyRSKtools, the RSK is actually a reference pointing to the real object. Like when you do raw equal RSK, this is not copying this real object, it's copying the reference to this object. So when you do post-processing and you modify this project, this raw data will change as well. That's why we developed a function called RSK copy. So instead of doing this, you want to do raw equal RSK dot copy. Yeah. And this I find is the most useful two differences that our user easy to getting confused. Okay, so I'm going to go in back and share my screen. Yeah, and there are some other difference like the exports. So MRSK can export to both RSK, CSV, ODV, the CBIRD format, and MAT file. PIRSK only export RSK to RSK and RSK to CSV. And for plot, in MATLAB, you can simply just open the hold on and keep plotting on the existing file. But for Python is not that flexible. So there is a function called RSK.merge_plots that can help you merge the two plots together. Yeah, and there are some other differences that we can touch in the demo. Okay, so let's start looking at this demo. The first step is always import modules to set up the environment. So if you do from pyRSK's import RSK, and in this demo, I also use NumPy and matplotlib. Okay, let's run this really quick. And this is some files that I'm going to use in the demo. Okay, to read the RSK files, there are two ways. So first is to just simply do rsk.open, and this gives you the connection to the RSK SQLite database. But if you're using this method, please do remember to close it properly. Because if like people are editing or doing the job on the same file at the same time, there is a chance that the file could encounter corruption. Okay, so here after we do the open, we just do like print channels, for example, give an idea like, so this is the RSK concerto and the serial number, the sample rate is 8 Hertz. And then this is the channels, the existing channels. And if you print RSK, it shows like what has been populated after we do the RSK open. There are some like internal state and informational attributes and the computational attributes like the data hasn't been really populated when you do the open. You have to do like rsk.read data to really get the data. Okay, there is another way to do the file open, which is we recommend it, is to use the with statement. This way you don't have to worry about, you don't have to remember like, did I close the file properly? Yeah, so here is an example. Because we removed the downscale samples, and if your data file is really large, so here there is an option that you can specify the start time and end time and only read the data between the start time and end time to save some memory.
I don't want to interrupt you, but I did see a question come in. Would you like to ask it?
Yeah, sounds great.
Okay, great. So the question is, I'm not familiar with the RSK data type, and here it is described as a structure, like a MATLAB structure. Is the RSK handled in pyRSKtools as a net? Oh my God, I'm not going to
net CDF or okay. So actually we have some better information documented in our online documentation. You like if you're a MATLAB user, you can consider it like a structure. It basically includes the following information, like the file names, version, log, and like all this stuff. So it's not a netcdf, but it's an object like this. Is it clear to you?
Great, thanks, Chi. I don't know who asked the question, but if they'd like to expand or if that wasn't clear, please feel free to raise your hand or type in a new question.
Yeah, exactly. Thank you. Okay, so let's go back to our demo. Okay. So here is showing exactly the same information. And here I'm just to give you some examples. This is like what kind of this channels included in this file, and timestamp structure. Yeah. Okay, so this is the part I just mentioned. The profile structure is different from the MRSK. So if you want to get a profile, you need to get the profile indices. This is get the profile indices for the first profile number 1, with both downcast and upcast specified as direction. And this is the way, like how you get the profile data. Yeah. So after that, we can move to the processing part. Let's just take a quick look at what kind of post-processing methods included. So I got a question asking, like, do we have a written up code for CTD processing? I don't have one, and also like it also, like, the parameters varies based on different application. So I think instead of a code, it'd be great to include a summarize here to show a simplified CTD post-processing pipeline. So first you open the RSK file and read data by using these functions. So sometimes if you don't trust the profile included in the data set, you can always calculate the profiles by calling this function, and then get the profile indices. And to visualize the raw data, this just to give you a quick look. So plot profiles is plot profiles visualization, and the plot data is the time series visualization. Calculate, then derive some useful channels like the sea pressure or depth. So for the sea pressure, we offer the option to input the atmosphere pressure. So by default, it's just use the value 10.1325. But you can either input your own value, or you can input a list of atmosphere pressure data. This is useful because like our customer from China, they monitoring the wave data to study the coastal wave attenuation. And during their deployment, they encountered a low pressure event. And at the very beginning, they thought there is something wrong with the measurement. But then after they applied atmosphere correction to really input the time series of the atmosphere pressure, and then they got the correct result as they expected. So this is the neat part. And then you can clean or low pass filter the conductivity temperature using smooth. We offer 3 different smooth method: the boxcar, median, and triangle. And also you can also trim your redundant data or do despike to get rid of the outliers. And for the despike, yeah, I remember like one question I got from the register form is, do we have the QA/QC capability? So currently we don't have a specific function for QA and QC. But this spike can somehow be used as a QA/QC tool, because it allows you to set up a threshold. Threshold is the amount of standard deviation between the reference data and your real data. And that's the way you identify the outlier. And this dspike function can output the indices of the flagged data. Yeah. And then it's important to align the temperature and conductivity, especially for the applications with the sharp salinity gradient. And there are 4 useful functions that we provided for this dynamic correction, and I will expand this part later with more details. And we can remove the ship heave and then derive some other variables like salinity, theta, the partial salinity, sound of speed. And speaking about the sound speed, there is one question asking that, do you have code to correct ADCP range bin locations and vertical velocities using measured CTD data? So for these questions, the short answer is we don't have code to correct ADCP range bin locations, but you can use this RSK derive sound speed to do the to get the profile of sound velocity, so that you can use for this correction. Okay. And then you can do the bin average. You can either average by depth or average by time. And then you can visualize the processed data by using plot profiles, plot data. RSK images is to plot the 2D distribution, and also plot TS is to provide the TS diagram and export the file to different format as needed. Okay, so we still going back to this demo to show how it looks like. So here I just derived like 4 channels. And if you remember, when we print the channels, previously we only got 7 channels up here, but after you derive channels, you can see like more channels is appended. Okay, and let's just take a quick look at how this data looks like. So here it plots. So here I'm doing some trim because I get some redundant data at the surface. And now I'm plotting the profile of temperature, salinity, and chlorophyll channels. What I plot is the upcast, and I plot the first 2 profiles, which is showing here. Okay, and here the plot data is to plot the time series. Yeah, this is just a quick look. And the time series, you can also open this show cast equal true. This will gives you, this will mark the downcast and upcast. Okay, so process. Like before the process, this is what I mentioned, like I want to keep the original data by using RSK copy. Okay, first let's try remove loops. So, you know, like ideally we want to get a smooth profile like this, but that's not the real world. If the wave is high and your ship is getting up and down, you more likely getting this messy profile. And remove loops is to get rid of this part. So the way it's doing it is include two parts. So one is it allows you to set up a velocity threshold. So once it detects the velocity is smaller than a threshold, it mark it as it flag it as a loop. Also, when it so if this is a downcast, and there is already if it detected some reverse pressure, like the pressure already shown before, it will also flag this part as a loop. So doing it in here, yeah, just run this quickly. Okay. So this is not a perfect example. This is actually like before the deployment, like the ship is still drifting. So the best way for this case is actually trim the redundant data. But I just use it as an example to show remove the heave. And the threshold, the velocity threshold I set up is 0.1 meter per second. And if I optimize the threshold, it will give you a more clean result. But here is just show the idea. Okay, and this is the demo for the low pass filter. So here it allows you to choose which channel you would like to smooth and the window length. Okay. So blue line is the original data and green line is the processed data that is getting smoother. Okay, CT correction. This is a important part I want to show. Okay, as I mentioned, like if you are doing the profiling with at a region with sharp gradients, sometimes you get the salinity spike, because the salinity is a derived channel that calculated based on temperature and conductivity. So there are several causes that can drive this salinity spike. So first is like the temperature. It takes time for the heat to diffuse through the thermistor stream. So let's say if there is a step change, which is this red color line, that's a true temperature. But this black line is the measured temperature we got. So here, it takes time for the temperature to diffuse, and second, the temperature, the thermistor time constant, like our faster thermistor time constant is 100 millisecond, less than 100 millisecond, and this will also dampen some high frequency signal. So this is the correction that we want to implement to improve the data. And there is also cause from the conductivity channel. Like if you go from cold water to warm water, the exchange of the heat between the conductivity cell and the water around it changes the conductivity, because the conductivity is highly depends on the temperature. So you can get like true conductivity change like this, but the real measurement looks like this. So in these two cases, the temperature and the conductivity, we want to shift the lag and optionally restore the high frequency energy that could potentially dampen because of the time response, the sensor response time. There is another cause that we is the misalignment between temperature channel and the conductivity channel. So first, there might be a spatial misalignment caused by the sensor itself, like meaning it is not measuring the water parcel at exactly the same time. So you can see this black conductivity cell. This is our old version conductivity cell. And it has the thermistor mounted on the sensor end cap, which has like physically has a location different between temperature and conductivity. And the right panel shows the with this red conductivity cell, you can see the thermistor is right beside the conductivity cell. This is the way we want to improve the profiling data. And even with this design, there still could be some lag between temperature and conductivity because of the different sensor response time, because the conductivity response time, the conductivity sensor is generally way faster than the thermistor. So for this cause, we want to shift in time to adjust the phase lag between the temperature and conductivity channel. And pyRSKtools provide this for function. Calculate CT lag is a method you can use to get the best CT lag recommended. And the align channel is to just align CT channel, and correct TM. This is thermal mass, is taking care of the heat diffusion. And this RSK correct tau is the one I mentioned to restore the high frequency energy. Like this tau means the temperature, means the time constant. So and here are some examples to show how you can use this for functions for the dynamic correction. This is not a recipe to follow, like we use first, second, like to correct your dynamic corrections, always following these 4 steps. This is not a recipe like this. This is just examples to showing like how each function work. So for the calculate CT lag, there is an important part to let you choose the C pressure range. And this C pressure range is ideally to be set up as the range where you expect to see a sharp salinity gradient. And here it specify which profile it is dealing with, and whether you're going to correct upcast or the downcast. And the align channel is shift. So here is an example to shift the temperature ahead by 40 milliseconds. So if you want to shift ahead, then please add a minus here in the lag. And for the lag units, we have 2 different options. Here you can shift by seconds, or you can shift by samples. The default is samples. RSK correct tau is to sharpen the signal with this algorithm. And also the correct thermal mass is following this popular algorithm. And if you have questions on setting up these parameters here, I would recommend you also check back in 2020, there was a webinar provided by our oceanographer, Mark Harrison. He talked more details about the dynamic correction. And recently, our oceanographer, Matthew Denver, also published a paper that's more about the 2000 deep Argo CTD correction. And he's actually going to give a talk on next Thursday at the ADMT meeting. So yeah, just feel free to check. And this is a dynamic correction example provided by our customer from APL, University of Washington, is collecting their data grabbed using the Sea Glider. And you can see by this salinity, the red line is the corrected version, and it improves a lot. Okay, so I'm going to show you a demo here to do the CT correction. Oh. This file is a bit bigger, so it takes a few seconds. Okay, so here I copy the original one and do the derived salinity for the original, for the raw data for our comparison next. And then here, the ideal, the time lag is 0.35 seconds. So I apply these to the lag, and then do the channel alignment. And here shows the result. So the red line is the raw data, and the blue line is the corrected for CT lag. You can see the salinity spike up here is greatly improved by moving the temperature channel align with the conductivity channel. Okay, so other than that, we also provide, like this is example for the bin average. Here, it allows you to set up the bin size and the boundary. This boundary is, let's say this is a downcast we're looking at, and you want to start a bin average since 0.5 meter. And it gives you an average, like every 5 dbar. This is the bin size I set. And also, for some deep sea application, you don't want to uniform the bin size. You want different bin size. So here also allows you to do that. You can set different size. Like at the surface, I want a bin size of 2 dbar. And if we go deeper, I want 10 dbar as a bin. And this boundary is telling you from 0 to 50 meter, I want a bin size of 2. And from 50 to 100 meter, I want a bin size of 10. And if we run that, we can see it binned by different sizes. Yeah. Okay. So about view, I've shown like how the plot data and plot profiles use above. And here is an example of the TS diagram. Still, you can specify the profiles number, upcast or downcast, and the difference between the isopacnol. And other than that, we provide a 2D image. Just before you do the RSK images, you need to do the bin average first. Okay, so the first plot, is just showing a 2D image. But sometimes our profiles, like you're moving from station by station, like the profiles are not taking continuously. And in this case, you would like to open the show gap equal true. And it allows you to show like the gap between two series of profiles. Okay. And that's pretty much everything about the demo. So our next steps is going to like support the Sara seawater library, because some of our customers, they prefer to use this old library, and they think when deal with large data, it works faster. And also we are going to support more RSK versions, including some of the old versions. And also currently our PIRSK has an assumption, which is a bad assumption, that it requires the equal numbers of upcast and downcast, and we're going to fix this to allow like different upcast and downcast, because they not always showing as a pair. Okay, and then I think we can move to the Q&A session. Oh, sorry, I'm talking too much.
Great. No, this is great. Thank you so much, Chi. I think you really answered a lot of the questions that people had submitted before in the registration process. Yeah, we'll open it up now to the attendees to enter things in the chat or the Q&A. I'm happy to read it off and moderate. I know that there were a couple other questions that were submitted in advance that we can kick it off with if you'd like.
Yeah, sounds great.
I think you pretty much answered these. How to process pressure data into wave parameters.
Oh, okay, right. That's the one. So currently our wave parameter processing is still in Ruskin, which is our software. RSKtools don't have the capability to do the wave processing. And I saw one of the question is to ask like how we implement the wave processing. This is well documented on our website, but I also want to give a basic idea or procedures like how it is implemented. So first, when you get burst data, because the logger with the wave mode allow you to sample as burst. So first is remove the depth mean and detrend the burst data. And then apply a hanging window on the burst data. I think the window size is 96 samples to minimize the spectral leakage. And the third, it applied discrete Fourier transform to transfer the data in time to data in frequency. And then it apply the attenuate correction to restore the full data spectra. The reason we do that is because, you know, like the this is the surface, and the wave will always dampen or attenuate with depth. So let's say if your deployment depth is here, and when you get a spectra, you want to do the attenuation correction to include full power spectra. And then it apply the inverse Fourier transform to translate back to the time series in time. And then it applied the zero crossing statistics to get all the wave parameters. Yeah, that's pretty much, yeah. But I can send out the link with the exact step-by-step and the full documentation.
That would be great. And we can send that as follow-up too. That was super helpful. All right, we have 2 more questions that came in. The first one is, when you extract the individual up and down cast, do you do any analyses on a cast by cast basis? For example, looking at sensor drift after many casts.
We are not really doing this. And can I have more context? Like, what's the purpose to?
That's all in the Q&A, but
Oh, okay. Yeah. So if it it'd be great to have more context to really understand what the what the customer expect. And as I mentioned, so our RSKtools is not just to stay as is. It's going to add more functions based on your need. So if you find that's helpful to detect the drift, that's also a great idea that we can consider to add into the toolbox.
okay. And whoever asked that, let's see who they added more context, and feel free, I can unmute you as well. But they said the context was, after a long cruise, sensor electronics tend to drift and they need to be recalibrated. Can you assess how much the drift has occurred by the casts?
By the cast
Or
time.
It has occurred by, yeah.
Yeah. So like we have so like in our specs, we have, I think, for the temperature channel, the thermistor, we have pretty low drift. Like the annual drift is 0.00002. It's less than that. So like it really depends on like which sensor you're talking about. But for the pH sensor, it does drift. Like typically we won't recommend like a really long deployment with the hydronaut pH sensor because the drift could really affect the observation. Like it's on the scale of months.
Okay. And I just, for the audience, I allowed you all to talk. So if you want to unmute yourself, you're welcome to. And we can move on to the next question unless anyone would like to ask or further expand on that. All right. So the second question is, thank you, Chi. When you visualize the data at the beginning of your routine first, what are your key statistics?
Visualize data at the beginning of your routine.
Not sure you understand the question.
Yeah, I'm not sure I'm understanding the question clearly. So if you just want to take a quick look, like I just use the plot profiles or plot data to look at, like, let's say if you plot the time series, you can easily identify if there is some like unexpected outliers that you observed. Statistics. So as I mentioned, if you want to go a bit further, just clean up a bit, like remove the loops, like smooth the data by low pass filter, and yeah, these are pretty much what I did.
Okay, great. Those are all the questions that I've seen come in, but again, everyone is allowed to unmute themselves. I've given you the functionality. So
yeah. Oh, and I also see there is one question hasn't been covered. It's asking about merging the data from various RBR and auxiliary sources. So I'm not sure if I'm understanding this question correctly. From my understanding, it seems more related to data file format converting. As I mentioned, like there are two ways to do it. So when you read the file, you can convert the CSV file to RSK file. And when you export, you can also export the RSK to CSV. Or if you prefer to work using the RSK files, then like you can like import the data and use RSK create to create like a RSK file structure and then output it as RSKs. This can sort of like merging data from different sources.
Great. Thank you so much, Chi. Well, if we don't have any more questions come up, I really wanted to thank you so much for your great, Aaron wants to unmute. Go ahead. You should be able to unmute, Aaron.
Hi, Chi. Thank you.
Hi.
I had a quick question.
Sure.
I don't use RBR sensors very often. Do you by any chance happen to have practice data sets that are available
Yes.
for running through this?
Yeah, that's a very good question. So in our, you can find a data set either from our Bitbucket repo. There is a file called sample.rsk. That's the file you can play with. And there is also, like in our documentation, you can find, I'm going to send you the link after the meeting so that you know where exactly it is.
Cool, thank you.
No problem.
Great. Anyone else? Any other final questions for Chi? All right, Chi, well, I think you gave a really comprehensive, incredible talk, and I know there'll probably be a lot of follow-up conversations. So I'm happy to facilitate any of those or share any links. And again, for all of you that are attending, thank you so much for your time and participation. We really value your feedback and would like to hear what topics and companies you would like to hear from in the future. So please feel free to reach out to me or Douglas Alden to submit those. I know that we are also working to have some in-person technical talks early next year. I believe RBR will be back with some new instrumentation in February. So again, would love to hear your thoughts and requests on in-person technical talks too. So with that, I will just say thank you to everyone, wishing you all a wonderful weekend and a happy, healthy holiday season. Thanks again, Chi.
Thank you.
Bye-bye.